Yeah, I'll just grab some from someone. Okay guys, today we're going to be talking about precipitation chemistry. Precipitation chemistry. Tomorrow there is supposed to be some rain. We call it
Precipitation.
Precipitation. To precipitate means to
Come down.
yes, or fall out of. To fall out. Huh? So precipitation chemistry involves the formation of a precipitate. Okay? Now, unlike rain, rain's a solution, isn't it? It's wet, it's water, it's a droplet, it's falling out of the sky. This is as far as the analogy goes. Precipitation chemistry, you actually have a solid, okay? You have a solid ionic compound falling out of solution when two solutions are mixed. That's all we're talking about. I'll say it again. Precipitation happens when two solutions that contain dissolved ions are mixed. Under the right circumstances, they will form a precipitate, and you'll see it happen. So, everybody ready for some chemistry magic? Everyone loves a bit of chemistry magic. I just place this harmless solution. See that? Clear solution. Everyone look at my solution. There it is. Clear solution. Now, it's not water. It looks like water. It contains some ions. Remember, dissolved ions. These are elements, atoms, that have lost or gained electrons and have an electrostatic attraction. But at the moment, the electrostatic attraction of the anion and the cation in this solution has been overcome by the polarity of water, the solvent, and they've been pulled apart. They're floating around as aqueous ions. So imagine an ebony as little positive and negative particles floating around in solution, right? They're there, you just can't see them. So I'm going to put some of these ions that currently aren't colliding into this conical flask right here. And they're suspended there in this solution. There we are. Now, I have another volumetric flask here that looks the same, doesn't it? It's containing some ions, and they're floating around in there, and their electrostatic attraction for each other has been overcome by the solvent water, and they've formed a solution. They're aqueous ions, they're floating around, you can't see them. You don't know they're there, I'm just telling you that they are. You'd have to do other tests to prove they're there. But when I've taken this particular solution, and this solution that contains its ions, and I mix them, watch what happens. I form a? No. A precipitate. Precipitation chemistry. How cool is that? In there, I've got a huge colour change, so it's a chemical reaction, right? I also have formed a new product. If you have a look around there, you can see all the sediment sitting on the bottom. See how now it looks like a really bad orange juice? Like lots of the original orange juice. See how it goes? See the particulate sitting on the bottom? Right? A solid particle has suddenly fallen out of this solution. See all the solids? Okay, that yellow colour is a solid precipitate. It's got a unique colour. Most precipitates are white, but this is one of my favourite ones. That's why I did it, Lamborghini yellow. This precipitate here is actually lead iodide. Lead iodide. It's a solid which, when lead ions can find iodide ions, will form and falls out and goes yellow. It's a super example of precipitation chemistry. Pretty cool? Okay, so what we have there is evidence of precipitation. So let's think about it. In this volumetric flask here, the first one, I had some potassium ions, they were positive, and I had iodide ions. Now, potassium iodide is obviously aqueous. See, they're floating around in there. They don't form a precipitate. They stay in solution, so that's important. In this volumetric flask, I had lead nitrate. Now, forget about the nitrates, forget about potassium. Let's focus on the two that did something. The iodide in here, when it was mixed with the lead that came from here, formed a new ionic bond which had more electrostatic attraction than the water that was keeping the ions apart in separate volumetric flasks. And it said, you know what, we're going to form a solid that water is unable to dissolve, lead iodide. And there it is now. It's actually settled out on the bottom, and if you looked up closely, there's a nice settling down the bottom of this sedimented precipitate. Sort of understand what's happening there? Mm-hmm. The most important thing for us in chemistry is that you're able to show this via chemical equations. You guys have been a little bit lazy with state so far, you've been able to get away with states. We sort of said, oh yeah, they're there. If you can put them in, otherwise don't. We're now at the point where with precipitation chemistry, it's all about states, because the states show you when a precipitate forms. And you need to be able to identify precipitate, and we're going to be able to predict a precipitate. And you guys are going to do your own precipitation prac tomorrow, where you start mixing different combinations to see what happens. Okay? This is a fun part of chemistry where it's really, really visible. So you've got your heading there, precipitation chemistry, don't you? Precipitation chemistry, and you've got your rules stuck in that I just gave you. You've gotten that far. Excellent, Ebony. So I'm going to now demonstrate what just happened, that we saw it, but using the chemistry, the language of chemistry in our chemical equations. Okay? So, under your heading, you've got to note down that states are vitally important. States are vitally important. That's a bad way. Mark, I'll see if we get a better one. States are vitally important. All right. Let's note down what's just happened. When a SLN, that's shorthand for solution, when an SLN, remember a solution by definition is the combination of a solvent, right, that's the thing that does the dissolving, and the solutes, they're the things that got dissolved. When they combine together, we say we have a solution. So in these two volumetric flasks, I have two solutions. There's water, that's the solvent, and there are dissolved ions, they're the solutes. Together they've made a solution of whatever it is we're talking about. So when a solution of lead, brackets, NO3 2 aqueous. When a solution of lead nitrate, Perv, is observed, it appears clear. It appears clear. In the primary classes, when they come up and I demonstrate chemistry to them to get them all excited about science, I tell them a little lie. I say, in here is just some normal water. Right? Now, it looks like water, doesn't it? This is highly toxic. It contains lead, bioaccumulative neurotoxin, right? Your body can't metabolize it. It inhibits your central nervous system function with enough concentrations. It can interfere with the development of the fetus in the womb. It can lead to inhibitions in the brain, mental retardation in children that are born from parents that have high levels of lead. Nasty stuff, lead. Right? We've moved away from leaded petrol to unleaded petrol because vaporized lead's even worse. So in this solution right now, I've got a toxin, it's lead, but you can't see it, you can't tell it's there. Right? It appears clear. Because in this circumstance, the lead ions are not partnered with any anions that have formed a precipitate. They've dissolved in this instance. So a solution of lead nitrate is observed, it appears clear. This is because the lead ions, which is Pb2+, and nitrate ions, which is NO3 1-, isn't that right, Pat? Yep. Have dissociated in water and are not bound together. You happy with that?
Yep.
The partnering of lead ions with nitrate ions is a partnering that water can interfere with and separate, dissociate, when water's added to that crystal. Lead nitrate dissolves, in other words, and it appears clear. Likewise, now I had iodide and it was potassium, so I've got Ki solution has dissociated. It's exactly the same situation. So in other words, if we wanted to represent it pictorially, it's like I've got a beaker here, and in one of the beakers, I've got lead ions floating around, and I've got nitrate ions floating around. And we'll put them in their ratios. These are aqueous ions. They are in water. AQ means, it comes from that root term aquatic, which means in water, AQ. Mitch?
I don't know what that is.
Yep. In the other beaker or volumetric flask, I simultaneously have a solution of potassium ions floating around with iodide ions. This is aqueous potassium iodide. However, when I mix the two, which we just did, when I add them together, I tip one into the other. Where have you been, Mitchie? Just grab a seat because we're in full flight. Okay. When I add out, and I'm recording this lesson because we've got lots of ways, so why don't you hop up there next to Pav this time?
Sorry.
When I tip them together, what happened? What was the evidence of chemical reaction? Yellow?
Change.
Colour change, particulates formed, I had a precipitation, a solid, an insoluble product. So really what we're saying is that I now have, in my bucket, a situation where I simultaneously have potassium ions and nitrate ions. Guys, these guys don't do anything. Interestingly, in here, potassium doesn't find nitrate to form a precipitate as well. We'll see that that remains soluble. Take your notes out, mate.
Yeah.
Take one of these tables. Stick this table at the top. And you'll be able to catch up. So I've got potassium and nitrate ions still floating around. Look at it. I've taken the nitrate. We'll just take one of them from here. And I've got the potassium from here. See how they've come from two? And now they're in the same fish tank, floating around independently. However, I also have something happening down the bottom. The lead, which had no affinity for nitrate in solution, has found iodide irresistible. Suddenly it's in a situation where it wants to partner up with iodide, and down the bottom now of this particular beaker, I have a solid. Remember I said states are vitally important? My solid lead iodide has formed. It's precipitated from solution, it's fallen out. The affinity that lead ions have for iodide ions, for some reason, and we'll get into this, is stronger and more water resistant than lead had for its original partner nitrate ions. So water here is doing a good job of keeping them apart. They're just floating around. They're like, you're more attracted to the water molecule than to each other. Put lead, though, into the vicinity of iodide, we're seeing, hang on, something happens. Lead hangs out with iodide in a way that water can't overcome. And I have a precipitate. Now notice, these guys are doing nothing. Right? Potassium started as a potassium ion, and it's still just hanging out as a potassium ion up the top of the beaker. Did nothing. Just floating around, looking around. What do we call that ion? Can you remember? We talked about going to the footy, state of origin, New South Wales wins, the crowd says, yay, we won. No, you didn't. They won. You just were a spectator. You didn't do anything. You watched the action take place. These are called spectator ions. They're there. They're watching the new game happen. They're not doing anything. They themselves don't change. So we're going to have, remember we've done our net ionic reactions and our neutral species complete. Remember that a little bit? Mm-hmm. So we can show now, not just pictorially what's happening here, we can show by using a chemical equation. Let's take a look at it. Ready? On the left, we started with lead nitrate. Now, Pav will tell you, you cannot just ignore Mr. Hazleton's crossover rule to make sure that you're getting your combination of ions correct, right? Week 3 of chemistry still stands. Don't just fall for the trap and say, oh, a lead and a nitrate ion, that'll be fine. No, it's PV, nitrate 2. The AQ tells you something. What does the AQ tell you, year 11? It's a solution that will appear clear. The ions are there, but they've separated. They're floating around independently. you're expected to be able to see that in AQ, it actually really means this. They are separated ions in water. They're actually not in there connected to each other like that. They're floating around in water. That's what AQ means. Now, I added that to potassium iodide, so I'm able to put K, which is in group 1, with iodide ions, which are in group 7, so it's 1 to 1. And again, these were AQ as well, weren't they? They were in a solution. Here they are, floating around happily. No precipitate or solid. They are aqueous. They are independent ions in solution. But with the combination, lead finds iodide irresistible. So rather than having two aqueous situations now, I have a component of my new solution which is not playing the game. It's breaking all the rules. It's saying I'm not going to stay in water anymore. I'm done with AQ. I'm going to form a precipitate. I'm undergoing a chemical change. Thank you very much. There's evidence of it because I changed colour and I've got a new particulate sitting on the bottom. You know what? Lead says when I'm around iodine, I'm going to just break all the rules. I'm not content hanging out in a solution anymore. I'm going to form a solid precipitate. I'm done with this water thing. And they leave the safety of water and form the yellow precipitate. So we show that simply by our understanding of saying lead, iodide, I2 is now an S. The S means solid. The solid fell out of solution, which means it's a precipitate. This is precipitation chemistry. All makes sense, doesn't it? It's just a bit of semantics. Now, what's left? Notice we have a new partner here. So these guys have a new partner too. I sometimes refer to it like a bush dance. You guys don't bush dance anymore, thank goodness. What a horrendous invention that was in Australia's history. But when you go to a bush dance, nearly the dancers are nearly always made up with you've got to find a new partner. This is a moment in the song we've been doing some weird thing and then it's like, hey, everyone swap over. Right? Precipitation chemistry is the moment of, hey, everyone swap over and see what the new partnership's like. One of the new partnerships is kind of like it was before. It's just still floating around a solution. But one of the partnerships has fallen out as a precipitate. So we've got to account for both new partnerships. This is one of them. The other one is actually a combination of potassium, that's the cation, so it comes first, and nitrate, that's the anion, it comes second. And you know what? It's still in solution. It's still just aqueous. They're still dissociated, separated. Just like over here, you were expected to know that these guys aren't really connected, and these guys aren't really connected. There they are. These guys are now connected and fell out, whereas these guys are still disconnected, dissociated. They're still aqueous in solution, floating around, doing nothing. They've done nothing. With me?
Yep.
What do I have to do?
Balance.
Balance. Good stuff. One lead. I'm pretty happy. Two nitrates. I've only accounted for one of the nitrates. They must be over here. There's nowhere else for them to go, so I put a coefficient 2 out the front. Now that I've got two potassiums, I must have had two potassiums, and by putting a 2 there, that really helps me out because I knew that I needed two iodines anyway. Who beat me to the balancing? Love it. All right. Now, this here is the chemical equation for the precipitation reaction. Okay? It's balanced. It shows where we started from, aqueous ions, and which one precipitated as a solid. That's great. Now, before we've walked through neutral species, complete ionic, and net, I'm seeing a lot of blank faces though. If I said to you that this is a neutral species balanced chemical equation, do you know what I'm talking about?
No.
You're a bit hazy. Okay. Notice there's no charges put anywhere here. None of them have charges written on them. But look in the beakers. I'm always putting charges on them. Right? A neutral species equation has, as an indicative part of the equation, charges there, it's just not shown. That's why it's called neutral species. We write the species as if they're bound together and they're neutral. Okay? This is a neutral species of lead nitrate. In water, I know it's not. It's separated into ions, but I'm able to display it here, and Maddie's expected not to fall asleep. But that there's positive 2 plus here and 1 minus there. The charges are hidden because I've combined them as a compound. This is called a neutral species. So let's put that there in the margin. This is a neutral species. We have done this, so I don't want to spend time on this. It's a neutral species reaction. There's another type called complete ionic. A complete ionic is completely over the top. A complete ionic reaction shows everything that's actually happening in the solutions individually according to the ions. Meaning, even though Mitchell knows that that's dissociated in their ions and we've just used some convenient chemistry to smush it all together, it now says in a complete ionic, I'm going to pretend that the person that I'm talking to is completely uneducated in chemistry. I'm going to show them exactly what I mean by this. I pull each ion apart and show it for what it is. So what I do is, Pav says, righto, well, lead's actually Pb2 plus aqueous. That's what's actually going on behind the scenes. I know it's Pb2 plus aqueous because I've said that lead nitrate's aqueous. So I'm just going to show that ion. Then I'm going to have to deal with the other ion. I've got 2 lots of nitrate aqueous ions. See how I'm just pulling apart that substance and saying, well, what I mean by lead nitrate aqueous is that both my ions are dissociated. See that? What do you think I'm going to have to do with potassium iodide?
Separate them as well.
Separate it. Oh, really, what I've got here is I've got 2 potassium ions and I've got 2 iodide ions. This is a complete ionic equation. It's showing each ion as if it's individualized in solution, which in fact it is on the left. Now notice, this is a solid which has fallen from solution and is no longer floating around in water. Its electrostatic attraction between the ions has overcome the interference of water, so this one stays together. Lead iodide, I do not pull apart and show its ions because it's the highlight of the precipitation. It's showing the precipitation in action. What should I do with potassium nitrate? It says here that it's still aqueous. What do you think I should do?
Separate it.
Separate it. I've got to show the 2 potassium ions aqueous and the 2 nitrate ions aqueous are still just floating around, looking around. It's like these guys have come to class, but they're just not switched on. They're not going to get involved. They don't want to do anything today. They just want to watch everyone else do the work. I came in as a potassium ion, leaving as a potassium ion. Fizz.
On the left, you wrote 2 potassium as the negative, is it?
Oh, finish the positive. There you go. Thank you.
Yes.
Good to go. This is a complete ionic reaction. It shows everything that is ionized as an ion and identifies when the precipitate occurs. Can you see how the most important aspect really is over here? You're saying, oh yeah, lead iodide's not ionized anymore. It's compound. What's the third one? The net ionic. Net ionic. Let's do the net ionic for the reaction. The net ionic equation. Who remembers our discussion about baked beans when you're a poor uni student? Can you remember?
No.
The day is coming when you're going to be a poor uni student. You have no money, you'll be studying, living the dream. And you'll be hungry. And you'll have $1 left. You go down to Coles or Woolies, IGA, and you say, I need to get some dinner, I have $1. And you go to the baked bean aisle, protein, sugar, all the good stuff. And on the can it'll say 400 grams net. What's that mean? 400 grams net. Don't say that. Say the opposite of what you just said. What does net mean? If you've got 400 grams net in your baked beans. Don't you guys do shopping?
Like 400 grams of just that one element within.
Think baked beans though. Baked beans is on
So
there.
400 grams of the baked beans with that.
400 grams of beans.
It's the mass of the beans, the stuff you want. It doesn't include the mass of the can. Now when you're really hungry and iron deficient, you might be tempted to eat the can and the beans, right? However, 400 grams net means, the mass of the stuff you're actually interested in here is 400 grams. And we're not going to tell you how heavy the can is because we know you're not buying this for the can. You're buying this for the beans. So the term net means just the stuff you're interested in when you buy cans. The net ionic equation in chemistry says just include the stuff we're interested in here. Just show me the ions that actually did something. In other words, it says get rid of the spectators and just include the ions that changed their form. That's what a net equation is, just the interesting stuff. So have a look. On the left, I had lead ions that started. On the right, they're no longer dissociated lead ions, they are lead solid. So they are included in my net ionic equation. Here they are, lead. On the left was an ion that's going to change. Now look at nitrates on the left and nitrates on the right. Have they changed at all?
No.
No. They went to the game, but they just spectated. They did nothing. They're there, but they didn't get involved. We don't include them in the equation. They are called a spectator, and spectators are not included in the net chemical equation. So we skip over them for now. We say, yeah, they're there on the left like this. They're still there on the right like this. They did nothing. I'm not putting them in my net equation. I'm not buying baked beans for the tin. Not interested. I'm so hungry, I'd eat it if it came off the floor. Just give me the beans. That's what we're saying. Where are the beans? Next one. Potassium ions. Are they beans or can? Can. Same on the left, same on the right, did nothing. Okay, how about the iodide ions? Beans. Aqueous on the left, solid on the right. Floated around happily in solution. Now they've fallen out of solution and changed colour. Used to be aqueous ions, free of any cares. Now they're bound forever to lead on the bottom of the beaker. They have changed, they've been involved in the reaction, they're important. These are the beans. So I've got to show them. On the left, I had 2 iodide ions, which were aqueous and 1 minus. But as they reacted, they found their new partner lead, and they formed a solid ionic compound that fell out of solution. Everything else is merely a spectator. Don't forget at year 11, neutral species shows everything clumped together, and it's the states that tell you which ones did what, neutral species. Complete ionic is completely over the top. It separates all of them into the individual species, but identifies which ions moved from aqueous to solid. Wake up, Mitch. Good boy.
I'm awake.
No, other Mitch. Mitch Mark 2. I just saw him do this.
Yeah.
Good man. Self-slapping is good in chemistry. The net ionic looks at the completely over the top one and says, well, which one of them are actually important? I need to separate the tin from the beans. I'm only going to show the ones that changed. So we need to now go in and let's just put a box around my spectator ions. This was a spectator. This was a spectator. How do I identify it? They are the same on the left as they are on the right. Absolutely nothing changes. They are, tell me their name? Spectator ions. Label them for me. All right. See how from a physical observation, the formation of a precipitate, we're able to put it into the language of chemistry and demonstrate what's actually happening at the ion level of collision. See that? It's pretty cool, isn't it? I think so. Now, so what? Well, you now should have a glaring question. Has anyone got a question that's haunting them at the moment in their head, given that I just showed you that?
I wish they draw us.
Mitchie?
I can't quite read.
Thanks.
Is that an iconic?
That's not the question. Ionic. Ionic.
Yes, but is it expandable iconic or is it
Ionic.
exfoliate?
Where, mate?
The middle.
Complete ionic.
Okay, I wasn't sure if it was complete or expandable.
Complete.
Thank
How
you.
on earth do I know? Fury, you had the question?
I think I know the question.
Go for it. Try it.
Is it, how come only the lead forms a precipitate?
Say that loud for the video.
How come only the lead forms a precipitate?
Thank you. The burning question should be, Hazelton, how can I believe you that you tell me, like just pass this around carefully, be careful there's lead in it. Just have a look now at how obvious the precipitation is formed. See that? Sitting on the bottom? It's a solid, newly coloured powder that's fallen out of the water. See that one, Mitchie? Look at that. It's obvious, sitting in the bottom there. That used to be a clear solution. No? See that one, girls? Just sitting down the bottom there? Look, it's very obvious there, hasn't it? It's managed to settle it out. Isn't that great? There it is. We could dry that, put in one of those bottles, and have anhydrous lead iodide and it'd be a yellow powder. And if you put water on it, it wouldn't dissolve. It's an insoluble activity. Very obvious. So your question should be to me what Fury just said, Hazelton, how do I know that's lead iodide and that it's not potassium nitrate? Because that's another option, isn't it? Right? If I'm playing the switcheroo and each partner gets the new opposite partner and one of them fell out, or how do I know it's not both? How do I know that that isn't actually lead iodide and that potassium nitrate is also a yellow precipitate that sits on the bottom of the beaker? That's a good question, isn't it? How could we tell?
Is the nitrate soluble?
Brilliant. I'm giving you a cheat sheet. Now, this cheat sheet comes from, originally in chemistry, doing heaps of tests and identifying which one obviously does do those precipitations. So we could pair them and pair them and pair them again and find out that in the end. And of course now we can get super precise and we can use something like atomic absorption spectroscopy that shows the concentration of lead ions changing over time. So we can prove that that is in fact lead iodide. But you guys are required in year 11 not to necessarily to go to that level of proof, but they want you to go to the level of prediction. Now I've given you this table from the textbook to stick into your books. They're going to ask that you are able to memorise some rules. Now be careful. This is one of those PAV moments from term 1, week 3. Okay? This is one of those polyatomic ion moments where I said, remember, you just got to know that nitrate's NO3 1-, it's a polyatomic ion, and everyone's like, yeah, we'll remember that, so it'll be fine on the day. And each lesson you're like, what's that one again? Okay. These rules need to become part of what we know about compounds. So let's walk through them because they'll help us make predictions. So on the left-hand side, we have the classes of compounds in your table that are soluble. What does that mean? Soluble.
They dissolve in water.
Dissolve in water. They dissolve in water. Lead iodide at the moment is no longer dissolving in water, it's insoluble. But here we're saying I've got two solutions that are made up of soluble ionic compounds. They've dissolved in water. They're clear. I hope that's clear. Now, Maddie knows from the table, no matter what, if she has a group 1 compound, it dissolves in water. No matter what. Group 1s. What does group 1 mean?
Elements on the periodic table that are in the first column.
Brilliant, Fizz. Elements on the periodic table that are in the first column, meaning no matter what happens, if your compound has a group 1 metal, it's going to dissolve. Meaning, all hydrogen, all lithium somethings, all sodium somethings, all potassium somethings, all rubidium somethings, all cesium somethings will always be soluble. You're expected to know that. I should be able to say to Ebony, hey Ebony, I've got this compound, it's called sodium, and before I say anything else, she's going, it's going to be soluble. It's a group 1 compound. It's going to dissolve. How cool is that? I love the groupings on the periodic table. It's like the ultimate cheat sheet in science. But you need to be able to remember that. Okay, so right now oh yeah, group 1s are always soluble. Now the best thing about science is there's always a couple of exceptions. Remember that great lesson where I said all of these metals in the middle here, they're always 2+, but you've got to remember silver, it's 1+, breaks the rules. There'll be a couple of little breaks, but these are general trends. So Pam, if I said to you, dude, I've got this great compound, it's called lithium sulfate, you'd be able to say, dude, that's going to dissolve every day of the week, guaranteed. And I'll say, why? So it's a group 1 compound. If I said to Mitch, I just found this really rare compound in the earth, it's rubidium phosphate. Mitch would say, well, it's going to dissolve. I'd say, how do you know? He'd say, well, it's in group 1, rubidium. Easy. Do you like that rule? I love that rule.
Mm-hmm.
So we need to be able to predict. Now look at what we used in our example. I used potassium, group 1, always dissolves, never falls out of solution. So straight up you can already tell me now, well, if that rule is true, that yellow precipitate can't be potassium. Because potassium's always dissolved. It doesn't fall out, never precipitates. It's like orange at the moment, never rains. Never precipitates. It's pretty cool, isn't it? What's the next rule? And ammonium compounds. Ammonium bromide. Oh, it's going to be soluble. Ammonium carbonate. Oh, it's going to be soluble. Ammonium acetate. Oh, it'll be soluble. Because it's an ammonium compound. You've got to get that one locked away. So you see how now we're pulling all this together? You've got to know your polyatomic ions. And then you've got to put them into these rules. And you'll be able to make these predictions. Okay? Nitrates are always soluble. You can't get a nitrate to precipitate out a solution no matter how hard you try. Huh? What about silver nitrate, sir? Soluble. Gold nitrate, sir? Soluble. Uranium nitrate? Soluble. Why? Because it's a nitrate. It never precipitates. That's pretty cool. And off we go. Now here's some exceptions. Chlorides. Where does chloride live? Over here in group 7. It's the opposite side of a big ravine. Here it is, chlorides, group 7s. Now all of the chlorides dissolve no matter what they are except for 2. Lead and silver. Now that's interesting because we just saw lead do something interesting. Lead iodide fell out of solution. So the chlorides are always soluble, except they do the same thing that lead just did with them. If you put lead around chloride, it's going to fall out of solution. And then sulfates, they tend to live in the middle ground. They've given you an example here. See how you assume solubility, but you've got to know 5 exceptions. Silver and lead are always exceptions. And then you've got these other 3 kicking in. Barium, strontium and calcium. They actually form the precipitate with sulfates. So I'd be able to say, hey Maddie, I found some barium sulfate. She'd be like, well that won't dissolve in water. That falls out of water because it's a sulfate but with an exception clause. See that? On the right hand side, these guys are always insoluble except if they're bound to the group 1 rules. So carbonates are insoluble. They fall out of solution. They don't dissolve. You find carbonates everywhere out there in nature. That's a large component of rocks. Now, do rocks always dissolve in the rain? That'd be a bit awkward, wouldn't it? They don't. Right? Full of carbonates. So you're getting pretty serious there. Did you go to bed last night?
Yeah, I was having a rough sleep because I had tea bed and I was moving
Okay, stay with me. We're gonna do 8 more minutes of
Don't worry, that worked out pretty good.
Yeah, it looked like it would have. Now, carbonates are insoluble unless you put them with group 1s, because the rule over here is that group 1s always dissolve. So if I have lithium carbonate, I've got a group 1. It's going to dissolve. But in the back of your head, you're going, that's exceptional for carbonate, because anything else with carbonate won't. Group 1 ammonia, same as over here. So if I said, you know what, Maddie, I've got a little sample of copper carbonate here. She'd say, let me just check my rules, sir. Just check group 1. Oh, copper's not there. Oh, copper lives somewhere insoluble, sir. Carbonates don't dissolve. See how easy it is? And you can see how it goes. Hydroxide and oxides follow the same rules, but they're even worse than carbonates. Hydroxide and oxides are insoluble all the time unless it's a group 1, because that's the rule. Right, so sodium oxide dissolves. Unless it's ammonium oxide will dissolve. Or unless it's barium, strontium and calcium, which were our 3 friends from down here. So they are. So barium hydroxide dissolves. Because barium's in the list that breaks the rule of the general behaviour. Right? Copper hydroxide does not dissolve. Because hydroxides don't dissolve unless it's one of these 5. See how to read the table? Therefore, you're going to be asked to make predictions. You're going to be asked to make predictions. So let's make a couple of predictions now as I set you loose. Are you ready? Keep your table in front of you for now. You're allowed to keep this table for a while. And then I'll have to wean you off it. All right. A solution is mixed with solution B. Here's A, here's B. Let's just do it on the screen together.
So should we write this
Nope,
down?
let's just do it on the screen together. On the left, I have a solution of copper nitrate. I'm never going to balance it. I'm just going to give you anion cation. How can I so confidently say that I have a solution of copper nitrate? Mitch? How can I so confidently say that that's going to be in the beaker as a solution and not as a powder?
Because nitrates are soluble.
Always. So no matter what that is, that's the solution. Nitrates always dissolve. How good is that? And I'm going to add that to a solution that contains sodium carbonate. How can I be so confident that that's going to be a solution?
Because sodium,
Say it, Pav?
sodium in group 1.
Sodium's group 1. No problem, sir. That's a solution. You've ticked all the boxes. I've got my 2 solutions. Now I'm going to add that to that one and tip it in. Will there be a precipitate? And if so, what will it be? Eb?
Carbonate,
Brilliant. How do you know?
because copper's not a group 1.
Copper's not group 1 and
And its carbonates are insoluble.
carbonates are insoluble. So I'm going to get a copper carbonate precipitate. The copper is going to find a new partner carbonate and it's going to fall out as a solid. Well, should I confirm that sodium nitrate doesn't just fall out as well, precipitate? How do I know it didn't fall out?
Because it's soluble.
It's got
Nitrates
both.
and group 1 are both soluble.
It's like doubly insoluble. Loves the water so much. This is the water baby, right? It's like the duck. It's like, I'm in heaven. I ain't ever coming out. Alright? See? Let's do the net equation for this just quickly. This one did nothing. That one did nothing. What are they called?
Spectators.
Spectators. They went to the game and just sat there and ate popcorn. Right? This one, however, went from on the left, it was an ion, and found carbonate, which on the left was an ion, and they formed a new relationship of copper carbonate solid. Quite literally, this exact situation would have happened, and we'd have copper carbonate sitting on the bottom. It, however, doesn't have the brilliant yellow. Only lead iodide does the brilliant yellow. Copper carbonate, quite sadly, is bluey white. Not as spectacular. See how it works? One of you guys give me a solution that you're confidently able to say would be a solution. Who's game? Just make up a solution from the periodic table. It's got to be a cation, anion.
Iron hydroxide.
Ooh, now hang on.
Hang on.
It's got to be a solution, champion.
Barium hydroxide.
Aha! Love how you corrected yourself there. How do I know that it's going to be a solution?
Because it has hydroxide and barium.
Brilliant. So hydroxide. See how I was awkward at the start? I was like, hang on. Hydroxide solution, that's rare. And what did you start by saying? You said iron hydroxide. I'm like, hang on, that's not in the list. That doesn't exist. That's not a solution, that's a solid. But then you self-corrected and said, oh, barium, which is it. Brilliant. What's my, okay, that's enough from Mitch. Someone over this side of the room, you guys are the second beaker. What solution would you guys like to start with?
Potassium sulfate, sir.
Potassium and some sulfate. Now, how can I be confident that Fury has given me a solution?
Group 1.
Group 1 metal. Pab loves that rule. All over it. Okay, so I've got 2 solutions. When I mix them, I'm swapping partners. Barium goes and checks out sulfate. Potassium goes and has a look at hydroxide. My new partnership, do either of them precipitate out?
Yes.
Yes.
Which one? Eb?
Potassium hydroxide.
Which one? What hydroxide?
Potassium hydroxide.
You reckon potassium hydroxide?
Yeah.
Okay, I love where you've gone because you said hydroxides tend to be insoluble and
Oh, that's a group
it's group 1. So here we are. Hydroxide saying I'm hanging to drop out a solution here,
It's barium sulfate.
but because it's potassium, I still can't do it. The other one?
Barium sulfate.
Why?
Because it is a sulfate, however it's got barium, so therefore it's insoluble.
So good. It's a sulfate which tend to be soluble, but the exception of barium kicked in and it dragged the sulfate out of solution, formed a white precipitate at the bottom of the beaker. Brilliant. So I got barium out of this situation. I ended up with a barium sulfate precipitate. See how it works? We've got to know the rules, apply them, and then use balanced chemical equations to show them. It's as simple as that. Now we get this great prac setup that I'm going to do with everyone tomorrow where you're going to do some physical testing for them. You'll have these two solutions. You know how to use the table, so you'll make a prediction to each other and say, look, when I mix these ones, I don't think anything's going to happen. So I'm not breaking it, bang, and then if something happens, you go, maybe I did that wrong. So that's where we're heading tomorrow. What I need you guys to do is really, really now, I've given you this massive overview crash course. It's absolutely vital that you start putting this together. What do we got? 1150, so we're going to have to pull up there. So take out, you've got your pen in hand. Underneath where we've been writing, I want you to go to page 238. Page 238 in your text. Page 238. I'm going to tell you the questions that you can now do. I want you to do question 2, 3, 4, 5, 6, 7 and 8. I think I just said 2 to 8. Is that right? Everything from question 2 onwards. Question 2 to 8. There's probably 40 minutes there. See you tomorrow.